Welcome to the new era of video creation with Bayozi. This is our new series on teaching deep learning. Today, we will discuss the object detection. Here are the contents. Object detection is one of the most important tasks in computer vision. It not only involves recognizing and classifying objects in an image, but also localizing them by predicting their positions in the form of bounding boxes. Unlike image classification, where the goal is to assign a single label to an image, object detection involves identifying multiple objects, even if they overlap or vary in scale. In practical applications, object detection is used in autonomous driving, security surveillance, robotics, and even medical imaging. For example, in autonomous driving, detecting pedestrians, vehicles, and traffic signs is crucial for vehicle navigation. In security systems, object detection can help identify suspicious activities. Object detection has two main challenges: localization, accurately predicting where the object is in the image; classification, correctly labeling the object. The key to effective object detection is the precise prediction of the bounding box, which encompasses the object in the image. Object detection consists of three main components. Localization. This involves predicting the coordinates of the object's bounding box within an image. The box is defined by its top left and bottom right corners, or by the center and dimensions: width, height. Classification. After detecting the object, the next step is to assign a label, such as car, dog, or person. The classification step helps to categorize the object correctly. Bounding boxes. A bounding box is a rectangular region that encompasses the object. The model predicts the four coordinates of the box, which is crucial for identifying where the object is in the image. Confidence scores. These scores indicate the model's confidence in its predictions. A higher confidence score means the model is more certain about the classification and localization. A well-performing object detection system needs to balance all these components, providing accurate and reliable predictions in real-time applications. In the early days of object detection, traditional methods relied heavily on handcrafted features and simple classifiers. One of the most common approaches was the sliding window technique, where a fixed-size window slides over the entire image, and at each location, a set of features, like edges or textures, was extracted. These features were then used to classify objects within the window. HOG, histogram of oriented gradients, was a popular feature extraction method used in traditional object detection systems. HOG captures the structure of local gradients and is sensitive to object shapes, making it effective for pedestrian detection. After feature extraction, support vector machines, SVMs, were typically used to classify the object within the window. While these methods worked in certain scenarios, they were slow and computationally expensive. Furthermore, the reliance on handcrafted features and the sliding window approach limited their accuracy and scalability, especially for complex or dynamic environments. The advent of deep learning has revolutionized object detection by automating the feature extraction process. Convolutional neural networks, CNNs, which are designed to automatically learn hierarchical representations of images, have enabled models to achieve far better performance than traditional methods. CNNs are capable of learning low-level features, like edges and textures, in early layers and progressively more complex features, like shapes, patterns, and objects, in deeper layers. This eliminates the need for manual feature engineering, significantly improving the model's ability to detect objects in a variety of conditions. Deep learning models also have the advantage of scalability. They can handle large datasets and complex environments, making them more robust in real-world applications. The introduction of CNNs led to a significant leap in performance, enabling real-time object detection, a key milestone for applications like autonomous driving and video surveillance. The RCNN, region-based CNN, was one of the first successful deep learning-based object detection methods. RCNN follows a two-step process: region proposal. First, a technique called selective search is used to propose potential regions in the image that may contain objects. This generates a set of candidate regions of interest, ROIs. Feature extraction and classification. Then, a CNN is applied to each of these regions to extract features. After feature extraction, an SVM classifier is used to classify each region into a specific object class. While RCNN achieved impressive results, it was relatively slow because of its two-stage process. The need to apply the CNN to each region individually was computationally expensive, which made it impractical for real-time applications. To address the speed limitations of RCNN, fast RCNN was developed. Unlike RCNN, which processes each region individually, fast RCNN applies the CNN to the entire image in one pass. This allows it to generate feature maps that contain information about the whole image, from which regions of interest can be extracted using ROI, region of interest pooling. ROI pooling maps the regions of interest onto the feature map, extracting fixed-size feature vectors from them. These vectors are then fed into a classifier and a bounding box regressor for object classification and localization. Fast RCNN significantly improved the speed of object detection, making it more feasible for real-time applications. It also allowed for end-to-end training, meaning that both the CNN feature extractor and the classifier could be jointly optimized for better performance. Faster RCNN introduced an important innovation, the Region Proposal Network, RPN. In previous versions of RCNN and Fast RCNN, the region proposals were generated using external methods like selective search. This process was slow and created a bottleneck in the pipeline. Faster RCNN solves this issue by using an RPN to generate region proposals directly from the CNN feature map. The RPN works by sliding a small window across the feature map, predicting the likelihood of an object being present in each region, as well as the bounding box coordinates. The RPN is trained jointly with the rest of the network, allowing the model to learn the best regions to propose for object detection. This approach eliminates the need for external region proposal algorithms, greatly improving both the speed and accuracy of the model. Faster RCNN became the standard for many object detection tasks due to its combination of high performance and efficiency. YOLO, you only look once, is a significant breakthrough in object detection because it processes the entire image in a single pass. Unlike RCNN and its variants, which use region proposals and a multi-stage process, YOLO divides the image into a grid and directly predicts bounding boxes and class labels for each grid cell. Each grid cell predicts the likelihood of an object in that cell, the class label of the object, the coordinates of the bounding box. YOLO's speed is its biggest advantage. It can run in real time and is suitable for applications where speed is critical, such as autonomous driving or live video analysis. However, YOLO trades off accuracy for speed, particularly when detecting small objects. The model tends to have difficulty with smaller objects that fall into a single grid cell, but newer versions like YOLO 3 have made improvements to mitigate this issue. The single-shot multi-box detector, SSD, is another popular object detection model. Like YOLO, SSD aims to detect objects in a single pass through the network, but it introduces a key improvement. It predicts bounding boxes and class labels at multiple scales by using feature maps from various layers of the network. This enables SSD to detect objects of different sizes more effectively. SSD is fast and provides competitive accuracy, making it a good choice for real-time object detection. The multi-scale approach helps SSD detect both large and small objects in the same image, overcoming one of the limitations of YOLO. However, SSD can still be less accurate than models like faster RCNN when it comes to small or overlapping objects. One of the challenges in object detection is the class imbalance problem, where the number of background pixels, or negative examples, vastly outnumbers the objects, positive examples. This can lead to poor detection performance for rare objects. RetinaNet addresses this by introducing focal loss, a modified loss function that gives more weight to hard-to-detect examples, such as small objects or objects in cluttered scenes. Focal loss reduces the relative loss for well-classified examples, focusing the network's attention on hard examples. RetinaNet achieves high accuracy and is especially good for detecting dense objects or rare objects in images, making it useful in applications like detecting small objects in satellite imagery or identifying rare species in wildlife monitoring. The introduction of transformers in computer vision has led to significant advancements in object detection. The Detection Transformers (DETR) model applies a transformer architecture to object detection, treating it as a set prediction problem rather than a grid-based one. DETR uses self-attention mechanisms to capture global context and relationships between different parts of the image. This allows it to handle complex scenes where objects interact with one another. The model directly predicts a set of bounding boxes and class labels, eliminating the need for region proposal networks or anchor boxes. While DETR achieves impressive accuracy, it requires large amounts of training data and computational resources, making it more suited for tasks where high precision is required. Object detection has a wide range of real-world applications that impact various industries. Autonomous driving. Object detection is critical for identifying pedestrians, other vehicles, traffic signs, and obstacles on the road. This allows self-driving cars to navigate safely and efficiently. Surveillance. In security systems, object detection can automatically identify suspicious behavior, such as intruders or unusual movements, enhancing monitoring efficiency. Healthcare. Object detection is used in medical imaging to identify tumors, lesions, and other abnormalities in X-rays, MRIs, or CT scans, aiding in early diagnosis. Retail. In retail, object detection can analyze customer behavior, track inventory levels, and even prevent shoplifting by identifying objects being moved or stolen. These applications demonstrate the importance of object detection in automating tasks and improving decision-making across various sectors. Despite the progress in object detection, several challenges remain. Object variability. Objects can appear in various sizes, colors, and orientations. Handling these variations is difficult, particularly when objects look different due to lighting conditions or environmental factors. Occlusions. In real-world scenarios, objects often overlap or are partially hidden behind other objects, making detection more complex. Class imbalance. The presence of far more background pixels than object pixels creates class imbalance, which can lead to biased predictions. Real-time performance. For certain applications like autonomous driving or surveillance, object detection needs to be fast enough to make real-time decisions. Achieving high accuracy while maintaining speed remains a key challenge. Overcoming these challenges continues to drive innovation in the field of object detection. The future of object detection is filled with exciting possibilities. Multimodal integration. Future systems will integrate object detection with other modalities like text and audio, creating more comprehensive AI systems. For instance, detecting objects while simultaneously understanding context through associated text could improve applications like image captioning and video analysis. Handling occlusions. Continued research will focus on better handling of occluded or partially hidden objects. Techniques such as contextual reasoning and multi-view approaches could help overcome these challenges. Edge devices. As AI moves towards edge devices, e.g., smartphones, IoT, there is a growing need for lightweight models that can perform object detection in real time with limited computational resources. This requires optimizing models for performance while keeping them small and efficient. Few-shot and zero-shot learning. Advances in few-shot and zero-shot learning could allow object detection models to recognize objects with minimal labeled data, improving adaptability across different domains. The future of object detection will see more robust, scalable, and efficient models that push the boundaries of AI vision systems. Object detection has evolved significantly, thanks to advancements in deep learning. Models like RCNN, YOLO, SSD, and RetinaNet have improved both speed and accuracy, enabling real-time detection in a variety of applications. Despite these advances, challenges remain, such as dealing with occlusions, object variability, and maintaining performance on edge devices. Looking forward, the integration of object detection with other data modalities, such as text and audio, will make systems more intelligent and adaptive. Research into few-shot learning and better handling of occlusions will likely lead to even more powerful and versatile object detection models. The future of object detection promises to bring even more robust, real-time, and scalable solutions for industries ranging from autonomous driving to healthcare.